This video is about acid-base reactions. So an acid-base reaction at its core is simply any reaction that transfers a proton from one thing to another. Comment here, we can actually just call a hydrogen ion a proton because once we've lost the electron from hydrogen, that's all it is. It's just a proton. Okay, so I use these terms interchangeably, proton, H+. These reactions are generally aqueous reactions, so they're in liquid water. So an acid is the substance that gives away the H+. The base is the substance that accepts the H+. Basically, those are the terms we're going to use for that. There are some different definitions for acids and bases, but those are pretty useful definitions here. Every acid-base reaction has both. You have to have, if you're going to give away the H, something's going to have to accept it. Okay, so every reaction has both. Water can actually act as either the acid or the base, and therefore sometimes you might have water being the base in the reaction, sometimes you might have water acting as the acid, depending on what it's reacting with. All right, so we have some definitions here. Strong acids are acids that fully react with water. They go to 100%. Weak ones do not. Okay, so acids all form H3O+ when they react with water. Essentially, the water is acting as the base, accepting that H+, forming H3O+. So HCl plus water goes to Cl- plus H3O+. This is a strong acid. The reaction goes to 100% yield. If you put HCl into water, 100% of that HCl will fall apart. The Cl will be left over. The H+'s will go to the water. Okay, so this is a little diagram. Probably hard to see on the video. If you want to look at this more carefully, you can look at the PowerPoint and maybe make it a little bit bigger. But you can see what's happening is we have little HCl molecules being put into water. Okay, when they're in the little squirty tube thing, they are the pipette. They are together. As soon as you put them in water, though, they separate. Okay, so HCl is called a strong acid. This is hydrochloric acid. We already know the name of it. It's also called a strong electrolyte. We've talked about electrolytes. So ionic compounds are strong electrolytes because they just fall apart into ions. Strong acids are also strong electrolytes because they form ions when they react with water. On the other hand, hydrofluoric acid, the difference between what I've written here and what I wrote above is, look, I've used a little funny looking arrow. This is an equilibrium arrow. It means the reaction does not go to 100%. Okay, the reaction only goes to about 10% yield. You can leave it there as long as you want. It is never going to completely fall apart. The little equilibrium thing actually means some of it is always actually going backwards, and then some of it's going forwards. It's sort of it's found a little dynamic equilibrium. So if it's a weak acid over here, and you may be able to see this on the video, you can see that even in the liquid there are some HF molecules that are staying together. Okay, so they are, unlike ionic molecules that totally fall apart, or ionic formula units, HF can stay, most of them, about 90% of them, are going to stay together and float around in the water like a molecular compound. Only about 10% are going to fall apart in this acid-base reaction. So HF is called a weak acid. It's also a weak electrolyte, so it forms a little bit of ions, okay? Not as much as it could, so it's called a weak electrolyte. Okay, so there are 7 acids that you have to know that are strong. This is really just memorization, but luckily there's 7 of them, and 3 of them clumped together in a group. So we've got HCl, HBr, HI. These are all the hydrohalic acids except HF. HF is an exception. So we've got hydrochloric, hydrobromic, hydroiodic acid, all strong. Okay, nitric acid, which is, the other ones don't necessarily go together as much, I guess. Nitric acid, and then the 2 chloric acids, so chloric acid, which is HClO3, and perchloric acid, HClO4, not chlorous or hypochlorous. Those are weak. And then the last one is H2SO4. This is sulfuric acid, battery acid. You might see it in everyday life. just want to point out here, there are 2 protons that could be lost. There's 2 H's written there at the beginning. Those can actually both be lost to water in an acid-base reaction, but only the first proton is a strong acid. After the second one gets lost, the second one's basically a weak acid once you've lost the first one. Okay, so there's 7, not that many. You are responsible for knowing them. And then any other acid you see is weak. Okay, remember acids generally are written so they're H's first. You know how to name a whole bunch of them. Pretty much, remember all of those acids that came from any oxo anion. All of those other acids are going to be weak. Okay. Strong bases also fully react with water, and weak bases do not. Okay, so bases all form OH minus when they react with water. It's a little bit of a interesting way to talk about this. So NaOH plus water, you can think about that as forming Na plus, again, plus water, plus OH minus. So these strong bases that actually contain OH in them, we usually just write without the waters on either side. But this reaction does go to 100% yield. Yeah, so we usually write it like this. We usually write acids as reacting with the water, but bases as just sort of falling apart, okay? So it's like, there's the weak bases we'll see in a second, that's harder to do. But so we frequently write them almost just like their regular ionic compounds. They simply fall apart. NaOH is a strong base. It's therefore also a strong electrolyte, especially if you're just thinking it almost like just an ionic thing. Okay, it's a strong electrolyte. Ammonia, on the other hand, NH3, when it reacts with water, we actually form OH by pulling the proton off of water. So in this case, you actually have to have water there to understand what's going on. So we have ammonia plus water forms ammonium ion plus OH minus, hydroxide ion. Notice again, I've used that equilibrium arrow. This reaction actually only goes to about 1% yield. Okay, so ammonia is actually one of the things, again, you might see this in everyday life. It's what gives like animal urine, it makes urine smell bad, right? But it's actually only going to about 1% yield. Okay, ammonia can also be cleaning supply, but it's actually a pretty weak base. Okay, because it's a weak base, it is also a weak electrolyte because it forms some ions, but not nearly as many as it could if it was completely falling apart like NaOH. Okay, so in terms of strong bases, actually memorization here is even easier. It's literally the group 1A metals with OH minus anions, so lithium, sodium, potassium, rubidium, cesium, hydroxides, and then barium hydroxide. So barium is the 2A. The other 2As would be strong bases if they could get into solution in water, but the rest of them are insoluble. So in practice, they just aren't really important strong bases. Just to point out here, there are 2 OHs actually in barium. So it's actually called dibasic. And unlike the H2SO4, where the first one gets lost and the second one becomes weak, this is basically just like an ionic compound. It completely falls apart all in one step. Barium hydroxide goes to barium plus 2 hydroxides. So both of them are considered strong. So we actually form twice as many OH anions as we would with like the same amount, the same number of moles of, say, NaOH. Okay, all the other bases are weak. There are generally not, there are not going to be any other ones with OH minus anions in them. They are generally going to be ammonia and variants of ammonia. So really, I cannot stress this enough, ammonia is a weak base. Okay, that's really the only one I'm going to generally expect you to know. Okay, and so then acids and bases can react with each other. We've kind of already seen that if we think about water being an acid or a base, but something that we might call an acid, like HCl and NaOH, can react with each other. Okay, so acids form H+, they really form H3O+, but you can also think about them honestly just like ionic compounds falling apart and the H+ floating around on its own. It's not what happens, but I think it's a little easier to picture in this case what's going on. So if we think of acids as forming protons, bases as forming OH minus ions, well, those things together make water. So when in acid-base neutralization reactions, we form water. Okay. Then whatever's left over forms what's called a salt. So we could have HCl and NaOH form water, and then with the leftovers are NaCl. This is what we think of as table salt, but lots of other things that we call salts in chemistry. H2SO4 and KOH form water and K2SO4. In this case, K2SO4 is the salt. Notice that because of that 2 in the H2SO4, we do have to double the KOH. We need twice as much base to react with it because there are 2 protons to neutralize. So I know that I said that second one was weak. That's only when it's acting with water. When it's reacting with a real base like KOH, it goes completely. Notice both of these arrows are complete. They're normal arrows. They go 100%. So even weak acids and bases react 100% with each other. It's just with water that they are weak. So just some examples here with a weak one. So HBrO2, not on a list of strong acids, so it's a weak acid. Okay, plus KOH, which is a strong base, does form H2O and KBrO2. Again, even though the HBrO2 is a weak acid, we're going to write that arrow. It's going to go 100%. We're not talking about weakness here. And then we also could have something like our weak base. Our weak base is ammonia plus HCl. In this case, okay, we don't actually form any water, because what happens is we transfer the proton from the HCl to the NH3. We make ammonium. We have the chloride left over. These actually just form the salt, is the only thing that happens. This is really the only time that happens is with ammonia or variants of ammonia, but just something to be aware of. There are, situations like this where we don't form water. And that's the end of this video.